Hello, I'm Dr. Vyvyane Low, and you are on vlmd Rounds, a podcast on medical science and tools to optimize your health. Now, I am not really enamored of today's topic. My patients and others have asked me numerous times to talk on this topic, and I've always resisted because I felt it's kind of messy. It's just messy. And I didn't really feel like this was a topic I could dig into, but they've asked me for many years, and I thought, okay, I'll just dig in and do an episode on non-nutritive sweeteners or artificial sweeteners, and that's what we're going to do today. Before I dive in, though, I just like to acknowledge someone, and this is Dr. Tony Hampton. He's a physician in the Chicago area, and we've known each other for a couple of years. Now, Tony has his own podcast. It's called Protecting Your Nest, and I encourage you to check it out. So I was here last night working on this episode, trying to get my notes together. As I said, it's not my favorite topic. It was New Year's Eve, raining. I was tired with a long week ahead of me coming up. And I was just thinking to myself, why am I doing this? Is this even helping anyone? Does anyone want to hear this? And it was right at that time that Dr. Hampton posted something on LinkedIn. And what he did was he posted a notice that kind of introduced this podcast and two other podcasts to his followers on LinkedIn. So the other two people were Dr. Akita Evans, and that podcast is called Health-E, and Dr. Andrea Salcido, and her podcast is called Conscious Gynecologist, and then vlmd Rounds, which is what you're listening to now. And he was just giving a plug, to all of us and trying to help us promote our podcast. I have to tell you, it was, as I said, late New Year's Eve. I was tired. And then I saw this, and I was really moved. He's a real pro. He's done this for a while. He's got over 130 episodes on his podcast. And for him to reach out and try to help some newbies along, I thought was a real class act. And I was very touched. So thank you, Tony, really from the bottom of my heart. And I just want to dedicate today's episode to him, which is a little bit ironic because I'm going to be talking about artificial sweeteners, so fake sweet. But I want you to know Dr. Tony Hampton is the real sweet, okay? So let's go. All right, so when we talk about artificial sweeteners, the first thing I want to tell you is that the biggest reason I just didn't want to do it is because we're really talking about a huge class of compounds, just different compounds with different biological effects and fates in our bodies, different metabolic profiles, and it's really not easy to make any big generalizations. And yet when you hear people talk about artificial sweeteners, oftentimes it's just lumped into one group. Artificial sweeteners, good, bad, whatever. Okay, so it's just not that easy to kind of get a grasp of. Now, obviously, they were developed because of the growing health concerns in this country with obesity and poor metabolic health. And I think the thinking was that if we can get people to use these sweeteners that don't have the same caloric values. So, we could get people to then maybe lose weight and manage their metabolism better. And so again, it's thinking along the lines of calories, right? And studies have been mixed. There were some early studies that seem to show that, okay, it's helpful, that people maybe do lose weight and control their blood sugar levels better. And then there are plenty of other later studies that have shown that, yeah, it's really done nothing. People are still continuing to gain weight, and we're really not managing their diabetes any better. Nonetheless, these products were developed, and as you can imagine, they had to be subjected to different types of testing because we want to make sure that it's safe for human consumption. So the tests usually were done on a variety of animals, animal models, so mice and dogs and rabbits and so forth, and then eventually in humans as well. And generally, they would take these substances and test them at very, very high doses. Okay, and the idea there was to try to figure out any potential toxic effects from those substances at those high doses. Okay, and this was also a chance for them to study the biological fate of those products. And in particular, they wanted to look at what they call the ADME, the absorption, the distribution, the metabolism, and excretion, right? ADME profiles of these substances. But then they also tested them at lower doses. Still fairly high, but not like the mega high doses. And the reason for that was they wanted to try and determine a dose at which there would be no observed adverse effects, okay, on the subject study. And this is important because this dose or this level, known as the no observed adverse events or effects level, okay, NOAEL, right? This is what is used to establish the acceptable daily intake, which is the ADI, okay? So it's the ADI, the acceptable daily intake, is based off of the no observed adverse effects level, right? And in determining the ADI, they look at that NOAEL level, NOAEL level, and then they also added in an extra safety factor. So, well, okay, we know that at this level we don't see any bad things happen, but let's just be extra safe. And oftentimes that safety factor was to decrease the NOAEL level by 100-fold. Okay, so if, for example, the no observed adverse effects level was 1,000 milligrams, then the ADI was going to be 10 milligrams, okay, because they would just divide it by 100. So it's set at a level 100 times lower than the NOAEL. So I just wanted you to understand how they come up with the ADI. All right, now let's talk about the sweeteners themselves. And so the way I thought about this was, okay, we'll kind of roughly divide them. It's not quite that neat, but we're going to divide them into, 3 main categories, okay? So we're going to look at those that are absorbed and not metabolized. That's one group. And then you have another group that is digested and metabolized in the body after absorption, okay? So we have that, and then we have one other group that is, usually thought of as not absorbed very much, but that group is also endogenous. In other words, your body also makes some of those chemicals, okay? So let's start with the first group. And as I said, that's the group where the substances are not really metabolized, even though they're absorbed into the body. The first one I want to talk about in that category is the famous ACE-K, acesulfame K, or acesulfame potassium, which is what the K stands for. I'm just going to call it ACE-K. And this was discovered in 1967. And apparently the person who synthesized this just accidentally, I guess, or somehow decided to taste this new compound. It wasn't like he was looking for a sweetener. He was not inventing a sweetener. He was just making something and thought, I'm just going to taste this. And my first thought upon reading that was like, why? Why would you synthesize some chemical and your first thought is, I'm going to taste this? But okay, I'll try not to ask too many of those types of questions. Okay, nonetheless, now we have ACE-K. So ACE-K is about 200 times sweeter than sucrose, which is your table sugar. So this means that you can use a lot less of ACE-K to have a comparable level of sweetness that you would get from table sugar. So for example, the level of sweetness that you would get from 25 grams of sucrose would only require 125 milligrams of ACE-K. So 25 grams of sugar, table sugar, that's about 6 teaspoons. And 125 milligrams of the ACE-K is 1/16 of a teaspoon. So you can see you do use a lot less. Now ACE-K is great because it's very soluble, it's very heat stable, and so it's used in a wide variety of processed foods, and it really resists heat degradation very well, and so that's why they like using ACE-K. The ADI, and the ADIs I will quote, will be the ones set by the FDA. There are different groups that set different ADIs, and just to be consistent, I'm just going to use the FDA ones. So the ADI for ACE-K is up to 15 milligrams per kilogram per day. So in someone who is 75 kilograms, that's about a gram, 1,125 milligrams per day. And just for you to get an idea, a 12-ounce can of diet soda that's sweetened just with ACE-K, that has 61 milligrams of ACE-K in it. Okay, so the ADI is about a gram, one 12-ounce can is about 61 milligrams. Now, if you went up to the max dose of about a gram, you would have to drink 18 of those 12-ounce cans to get that level of ACE-K. Now, the ACE-K is quite rapidly absorbed into the body, gets into the bloodstream, into the tissues, and it does cross the placenta, it does get into breast milk, okay? However, it is not metabolized prior to excretion by the kidneys. So it's absorbed rapidly, gets into your body, and then it's going to be excreted within 24 hours in the kidneys. Okay? There's a very small percentage that, gets into the poop, it gets into the feces, doesn't really get absorbed. But most of it is absorbed and then excreted by the kidneys unchanged. Okay, so the thing with ACE-K also is that a lot of times people are concerned about the K, and the K is the potassium, as I said. So sometimes I've been asked, do we have to worry about the potassium load in ACE-K if someone's drinking a lot of soda? So let's just look at that. ACE-K does dissociate into acesulfame and potassium. Problem is we don't quite know to what extent. It seems to be unclear there. Now, we've seen sweeteners that combine ACE-K with aspartame, and with those you do see them dissociate in aqueous solution. So the assumption is that with ACE-K, yes, you're going to have the ACE part, the acesulfame, dissociate from the potassium part. So how much potassium then are you getting? Now, a 12-ounce can of ACE-K could technically add a maximum of 12 milligrams of potassium to your daily intake. That's nothing, really, one 12-ounce can. If you went that max dose, remember I told you that would be about 18 cans of those, 12-ounce soda cans, then it would be 216 milligrams of potassium. Okay, 216 milligrams of potassium. I don't know why, but in the medical world, we use milliequivalents. And, through med school, in residency, everywhere, you're thinking in terms of milliequivalents. And I find that when I say milligrams, a lot of people get a little thrown off there. And it's not just doctors. I've spoken to a lot of nephrologists who were a little unsure of how to convert the milligrams to milliequivalents. And I've also talked to lots of pharmacists. And one time I was trying to get just different formulations of potassium, called like pretty much every pharmacy in my area, and nobody could do the conversion, right? So I'm just going to make it easy for you. The atomic weight of potassium is 39, all right? So you take whatever number of milligrams, divide it by 39, and that's going to give you the milliequivalence dose, okay? So that 216 milligrams is about 5.5 milliequivalents. And now that you've heard that, you're probably going, oh, yeah, because that's not very much at all, okay? So I don't think we need to worry about the potassium that's in the ACE-K. Now, that's in the diet sodas that only contain ACE-K, but generally ACE-K tends to be combined with other types of non-nutritive sweeteners. I just mentioned that, there are formulations that combine it with aspartame, for example, okay? But in general, it's in that category of it's absorbed and absorbed quite quickly, quite well, but it's really not metabolized, and then we just pee it out that way. Okay, now let's go on to the next one in that same category, and this one is sucralose. So sucralose is about 600 times sweeter than sugar, so it's a lot sweeter. And what's interesting is that its structure is really very similar to sucrose. In fact, it is sucrose, except that 3 hydroxy groups are replaced by chlorine. Okay. Now, when you say that, sometimes I've heard people say it's like bleach. Well, not really. I know there's chlorine in bleach, but there's chlorine in sodium chloride, right? So saline, and chlorine exists in your body as an anion. It's very important. So we do have chlorine in our bodies, or chloride, which, the ion form of it. And in fact, actually, your body also makes a little bit of hypochlorous acid, which is bleach. But this does not mean you can drink bleach. So please put that idea out of your head. No drinking bleach, okay? Your body makes small amounts of it under certain circumstances. Doesn't mean you should drink it, okay? But I just want to say that chlorine exists in your body. And in this case, it's replaced 3 hydroxy groups in the sucrose molecule to form, sometimes people call it trichlorosucrose, because it really is the sucrose structure just with those chlorine substitutions, okay? So that's how you get your sucralose. The ADI is up to 15 milligrams per kilogram per day. The brand name for sucralose that I guess most people are familiar with is Splenda. And I have mentioned in a previous episode that actually Splenda doesn't just have sucralose in it. Splenda has, maltodextrin and dextrin, so it has sugar in it as well. And it's not the pure sucralose. You can get the pure sucralose, but the brand Splenda is mixed in with sugar, okay? Now, the sucralose is not digested or metabolized, and even at pretty high doses, at 3,000 milligrams per kilogram, it's pretty hefty, it's excreted within 72 hours in feces. Okay, so it's passed out in poop. All right, but there have been a lot of concerns with sucralose. Now, the main concern I think that I have seen and heard about would be the changes to the gut microbiome. And I think this is the case with almost all of the artificial sweeteners. And this is one of the reasons this topic is so messy. The gut microbiome. Okay. So people ask me about that. Well, let me just go through this study first, okay? There's one study that was done in mice, and basically sucralose for 6 months altered the gut microbiome and fecal metabolites and increased the upregulation of pro-inflammatory gene expression in the liver, okay? And there are many studies like that about sucralose. And I will tell you that I'm pretty sure sucralose impacts the gut microbiome. I'll mention that a little later, why. But whenever I see studies on the gut microbiome and these artificial sweeteners, okay, number one, it's really hard to know what significance that has in humans. And that's because a lot of these studies, for them to do the dosing in the animal models, they're just doing a guesstimate based on the body surface area, the metabolic rate, and they're guesstimating and modeling it out. And then they kind of multiply or adjust it by some factor, and that's the dose often that they will use in those animal models. What that really means in terms of human dosing is really hard to tell. The other thing is, like in this study, for example, they said that they fed the mice sucralose for 6 months. Well, mice generally live about 2 years, 3, maybe, right? So 6 months is a significant amount of time in that lifespan, right? So how does this translate to human years? I don't even know where to start. I have no clue. Is it 6-month exposure for us too? Or is this some other, fraction of the lifespan? Who knows? I am not sure how to read that. And then, the other thing is that, okay, it changes the gut microbiome. I will tell you that almost anything will change the gut microbiome, which is why it's really hard to make sense of some of these studies. The gut microbiome is very dynamic. It's not static. There was a study that came out recently, and I think it was done in China, and they were following these adults for 3 years and following their gut microbiome, and essentially their conclusion was that, well, basically it's not static, it keeps changing all the time, and yeah, we don't know. And yeah, that's about right, because anytime you change your diet in any way, you travel, you go somewhere else, the ecology of your gut is going to shift, and it's not static. The other thing is, it's not 1 or 2 microbes that will, kind of impact your gut definitively. It's generally the ecology, right? The communal, response, the different organisms interacting with the immune cells, the intestinal cells, and so forth. So it's hard to sort out all these different pieces. And so I just find it pretty hard to take anything definitive out of the gut microbiome studies. Now, I definitely do think, there's a lot of interaction between our bodies and the gut microbiome. I just don't know what the specifics or the principles of that interaction would be. Okay, so for sure, certain certain products, certain things that we consume can cause our gut to have dysbiosis, and you can have leaky gut and disruption of the tight junctions in the gut, so that toxic substances can get into your body. That's for sure. And the immune response is very important as well. And these immune cells can signal the brain, that we've seen. And that kind of work I am really interested in, and I hope we'll do a lot more, because I want to know more about the immune cells, for example, in the gut, and how they talk to the brain and how they interact with microbes and so forth. But just looking at different species and saying, well, in this population of patients, we saw these species. I don't quite know what to make out of that. And one final point on this whole gut microbiome is, I just want to point out, if you all remember Ansel Keys, yeah, he was the guy who, did the 7-country study, and it really wasn't a 7-country study. He kind of did this study and said that, well, these countries, they ate a lot of fat, and there's a lot of, heart disease in the countries where they ate a lot of fat. And it turns out it was actually a 22-country study, but he just cherry-picked his data, okay? So we all agree that's a bad thing. And, 7 out of 22, that's about a third. So he only presented a third of the data. So if we consider that there's anywhere from 500 to 1,000 species in your gut. See, we don't even know. 500, 1,000, right? That's a huge range. And then even if you are talking about 10 species out of the 500 to 1,000, that's far less than 1/3 of the data. And I just can't make any kind of sense out of that, if you see what I mean, right? Because it's really only a small piece. And then, we have to factor in also how these species interact with others, and, under what circumstances, what the context is. So, I've gone on long enough about this, but when you're talking about artificial sweeteners, the main thing you're going to hear is about how it changes the gut microbiome. But yeah, almost anything you consume is gonna change the gut microbiome. And is it for better or for worse? I'm not sure under what circumstances, right? And also when you look at studies in, let's say, in animals, in this case, mice. Okay, one other thing I just want to point out is that mice are different in that mice eat poop. Okay, I don't know a whole lot about rodent biology, human biology, yeah, rodents not so much, lagomorphs maybe, cockroach, yeah, pretty good, don't ask. But rodents not great, but I know they eat poop. Okay, so I'm not even sure in some of these studies, did they make sure they didn't eat any poop? Because whatever you're dosing them at, if it's excreted in the feces, in the fecal matter, and they are consuming that, do we factor in that dosing, I don't know. I really have no clue. Okay, so, but, okay, now let's just go back to sucralose. I know we made this big detour, but let's just go back to sucralose. And here's the thing I want to say about sucralose that, really tells me it does do something to the gut microbiome. And it's actually when I was looking at the main concern on sucralose, and this was actually an environmental concern. And it turns out that sucralose really cannot be degraded. So once it's kind of pooped out, then you can't break it down any further. And so it's gotten into the wastewater, it's gotten into rivers and estuaries and the Gulf Stream, right? So we have this accumulation now of sucralose. And the main worry is that sucralose is bacteriostatic, and so it's going to change the microbes in the soil. Well, if it's changing the microbes in the soil, it's probably changing the microbes in your gut. That's a bit of a duh moment, okay? So I do think it is probably impacting some of the microbes and inhibiting the growth of certain species, and maybe, promoting the growth of other species as a result. But, to just kind of disentangle all the different pieces, we don't know yet. And I think that it's generally going to be, the higher doses where we're going to see maybe some significant changes in the gut. Okay, so that was my piece on sucralose. Saccharin. Saccharin is also one of those that gets absorbed, but it's not metabolized. It's 300 to 500 times sweeter than sugar, and the average intake is about 2 milligrams per kilogram per day. The ADI is around 5 milligrams per kilogram per day. It's very water soluble, and so it gets easily absorbed, especially at lower pH, which is what we have in our stomachs, right? So it turns out that 85 to 95% of the saccharin that you take in is going to be absorbed, and then it's going to be excreted in the urine. And then the rest is excreted in the poop. So not all of it is absorbed. If it's not absorbed, it's just excreted in fecal matter, and then whatever's absorbed is going to be excreted in urine, and it can transfer across the placenta as well. Now, the brand names for saccharin, I think, are Sweet and Low and Nectar Sweet, and also Sweet Twin. I'm not familiar with those two, but Sweet and Low, okay, is where you find saccharin. Okay, so that was the group of substances that are, well, absorbed, not metabolized. Now we're going to move on to the next group, and this group is where you find substances that are metabolized by the body, okay, digested maybe and metabolized, okay. So aspartame is in this group, the famous or infamous aspartame, which is a methylated dipeptide. Okay, so it's very sweet, and again, about 25 grams of sugar, the level of sweetness you would experience in 25 grams of sugar could be found in 125 milligrams of the aspartame, so much less, right? So again, 6 teaspoons of sugar, the equivalent in terms of sweetness would be 1/16 of a teaspoon of aspartame. It turns out the calorie content is actually the same as sugar, and it's 4 calories per gram. But because you need so much less, right, because it's so much sweeter, then whatever you find in the soda or in foods is really virtually, as they say, no calories, okay, because it's much, much less than what you would use in terms of a sugar equivalent, okay? So the FDA acceptable daily intake, or ADI, for aspartame is 50 milligrams per kilogram per day. In 2013, the average intake was about 5 milligrams per kilogram per day. And at the highest level of intake, the 95th percentile, it was at 13.3 milligrams per kilogram per day. So still quite far below the ADI of 50 milligrams per kilogram per day. And a more recent study is a European study of 17 countries. There, the average intake was 1 to 5 milligrams per kilogram per day. The aspartame is very quickly absorbed and digested in your body, mainly by aminopeptidase A and to a lesser extent aminopeptidase W. And these are just enzymes that digest the aspartame. And it's so quickly digested that really none of the intact aspartame gets into your blood. So it's absorbed and digested almost immediately. It's digested in the gut lumen, right? So as it's passing through the GI tract, but it's also digested in the intestinal cells. And it's as soon as it's absorbed, it's digested down into its three main components. And these are, 10% of the weight of aspartame is methanol, which is an alcohol. And 40% of it is aspartic acid, and 50% of it is phenylalanine. Now, phenylalanine and aspartic acid are amino acids, okay? So they make up proteins, for example. And you'll see when you have packets of aspartame that there's usually a warning that if someone has phenylketonuria, which is also sometimes just simply called PKU, that you should avoid using the aspartame. So phenylketonuria is a genetic disease, and essentially you don't have or have very little of the enzyme that is needed to metabolize or break down the phenylalanine. And then as a result, this builds up in the body and can be very toxic, especially to the nervous system, right? So in patients who have PKU, they can, if they accumulate too much of phenylalanine in their bodies, they can have seizures, right? They can also have, behavioral problems, emotional problems. They can have hyperactivity, developmental problems, okay? Now, the classic form of PKU, you just don't have the enzyme, or extremely, very, very little of the enzyme, right? And severely deficient. And those people will have the more serious side effects. And there's a milder form where they have some enzymatic function, but not enough, not the same as compared to someone who doesn't have PKU, okay? So when we digest the aspartame, we're going to break it down into methanol and 2 amino acids. So let's start with the methanol, and some of you already are thinking, ooh, that doesn't sound good. You're right, methanol doesn't sound good, and it's sometimes known as wood alcohol. If you consume it, let's see, 10 cc's of it, which is equivalent to 1/3 of an ounce, can cause permanent blindness, and 30 cc's or 1 ounce could even be fatal. So the reference dose for this is 0.5 milligrams per kilogram per day. Now, it's an alcohol, so of course it's a CNS, central nervous system depressant, but the main problem with methanol is its metabolism. And the methanol is metabolized by enzymes to become formaldehyde, and then that formaldehyde is metabolized by another enzyme to make formic acid. And formic acid is toxic to mitochondria. So, when we have a lot of methanol, we're going to basically kill off the mitochondria. And I don't know if some of you remember this during early days of the pandemic when there was a shortage of hand sanitizers, and some companies actually replaced the ethanol in the hand sanitizers with methanol, and that became a huge health concern because that can be absorbed. The methanol can be absorbed through the skin or ingested, right? And that could have caused a lot of serious problems. So as you know, we don't want to ingest methanol, you would think, right? I certainly don't want to, except we probably do every day in food, because methanol is also found in fruits, in vegetables. And look here, it says 1 can of tomato juice has 6 times more methanol than 1 can of soda. Okay, you can find it in fresh fruits, juices, vegetables, fermented beverages, and also smoked foods. I had smoked salmon the other day and I was thinking, probably consuming my daily dose of methanol. It's in sun-dried tomatoes and also tinned tomatoes as well. Okay, so we do have quite a lot more methanol than we realize in our foods. This is a paper that came from the Journal of Analytical Toxicology. It's called Estimates of Non-Alcoholic Food-Derived Ethanol and Methanol Exposure in Humans. And that's from March of 2022. I'm going to quote, it says, most foods produce higher methanol concentrations than the maximum allowable dose level, 23 milligrams, especially fruit juices, lead to the critical level of ethanol. This is different. This is ethanol, regular alcohol, for children at 6 milligrams per kilogram body weight. Okay, so another reason not to drink juices, right? I went on and on about this in the episode on fructose, but oh, look, you can get methanol and ethanol. That's what you're giving your kids when you give them fruit juices. And you think I'm kidding? It says here, another source, but it says average methanol concentration in fruit juices is 140 milligrams per liter. 200 cc's of juice has 28 grams of methanol. Told you, fruit juices are no good. All right. In humans, when they have dosed the subjects at 34 milligrams per kilogram per day, methanol concentrations were undetectable in the blood. Now, when they dosed them at greater than 100 milligrams per kilogram per day in a 60 kilogram person, then we did see some methanol accumulate in the blood. Now, I just want to point out this is equivalent to 12 liters of diet soda. Now, it's quite a lot, okay? And even people who are heterozygotes for PKU, remember, deficient in that gene for phenylalanine, at a dose of 600 milligrams per hour for 8 hours, they had the same levels of methanol and formate in blood and urine as normal people. So, you know, while you do not want to chug down wood alcohol, you know, we're consuming it in our foods every day, right? We just probably don't think about it, okay? So are we getting a mega dose from aspartame? I think it's unlikely, okay? So that is the methanol. Let's go to aspartic acid. Okay, this, as I said, is an amino acid. And the thing about it is it's absorbed pretty quickly, very quickly. And then even in the intestinal cells itself, it's already converted to oxaloacetate, okay? Oxaloacetate is one of the substrates in the Krebs cycle. So we have it in our bodies, and your body, it takes in the aspartic acid quite quickly and then almost immediately converts it to oxaloacetate. And then that gets picked up and goes into the portal circulation, goes to the liver. Now with animal studies, they've seen neuronal death at very high levels of the aspartic acid, but really for humans, it's metabolized so quickly. And that's the other thing with some of these studies, okay? IV, sort of IV delivery of the substance is very different from delivery through the gut, right? And nobody's injecting these substances into us, right? It has to be absorbed through the gut. So there are big differences there. Here, when it's absorbed through the gut, we very quickly convert it to oxaloacetate. It's pretty hard to accumulate aspartate levels in our body, okay? And then now, the third component of aspartame is phenylalanine, okay, the famous phenylalanine. And this is, again, absorbed quite quickly by the intestinal cells, gets into the portal circulation, and goes to the liver, where it is partially converted to tyrosine by certain enzymes, and also some neurotransmitters, okay? And these are things like dopamine and norepinephrine and epinephrine. And of course, this can go to the brain, okay? Now, excess phenylalanine is then going to be excreted in the urine. Of course, as I said, in people who have that defect where they are not able to process the phenylalanine and that accumulates in the body, then they're going to have neurological problems. But even then, in patients with severe PKU, after aspartame ingestion, they found that blood levels really were the same as their baseline levels and hadn't really changed very much. So, even in people who have deficiencies in the enzyme for processing phenylalanine, they don't seem to have huge changes based on, the aspartame ingestion. And now let's just talk about that study. Okay, that study is the one that has been making the rounds. It's PNAS Neuroscience, came out in a few months ago, October, I think, of 2022. And this was the one that said that, ingestion of small amounts of aspartame might be causing anxiety. So this was a mouse study, okay, and they gave the mouse equivalent of what they consider the mouse equivalent of 8 to 15% of the human FDA for 6 to 8 weeks. And these mice now started to exhibit, clear anxiety-like behavior. And they also found downregulation of GABA and upregulation of glutamate signaling in the amygdala. So very convincing here. And when they gave the animals Valium or diazepam, right, actually they calmed down. So the anxiety went away. So very convincing. And then even worse, in this study, it turns out that the dads, the male mice, actually passed down the anxiety trait down to the second generation of offspring, so down to the grandkids, right? So not only does this affect the mice, at least the male mice were able to pass the anxiety down 2 generations. Okay, so then I got asked, oh my God, is that what's causing my anxiety, Dr. Low? Probably not. But in reading the study probably did add to your anxiety. But let's look at this, okay? I don't know what to make of it. First of all, it's a mouse study. And again, I looked into this to model, what might be comparable in a mouse for, to a human being. There are various models. They pick one that they think works. And here, the model that they picked, the max dose for the mouse was 615 milligrams per kilogram per day. Now, the human ADI is 50 milligrams per kilograms per day. So I don't know how to read that, okay? And just for context, 1 can of pure aspartame containing diet soda has 200 milligrams of aspartame. And most sodas are actually sweetened with aspartame plus some other sweetener. But there may be 1 or 2 that are just pure aspartame, okay? And that would give you about 200 milligrams of aspartame. Again, with the mice, I'm not sure what to make of this. I think that certainly we have to pay attention to this, and I hope they'll do a lot more studies. Could it be that it's getting to the brain a lot faster in the mice? One of the things I learned from doing that episode on heavy metals, right, the lead and cadmium one, is that if you consume it, if you consume those metals with food or without food, it impacts the absorption. So, this was put in the water, but is this consumed without food? Does that make a difference? Does that make a difference for humans? I don't know. I have all these questions, right? I think they're good questions, but I think one thing we can say from this is that we can come up with a lot more questions and hopefully test those questions with further experiments. But 1 can of that diet soda that only contains, aspartame as the sweetener, as I said, has about 200 milligrams of the aspartame. But remember, those amino acids are found in food as well. So I said, well, what are we consuming? So in 100 grams of chicken, it turns out that the aspartic acid content is about 5,000 milligrams. And the phenylalanine content is about 2,000 milligrams. Okay, so just in 100 grams of chicken alone, that's how much of the aspartic acid and phenylalanine you're consuming. As I said, has this got to do with whether you're consuming it as a food, versus on an empty stomach? I think that's a good question. Again, the mice were exposed for 6 to 8 weeks. What's a comparable time length for humans, right? So those are the things that come up in my mind when I see a study like this. And obviously, I would love to see more research done on this, but I don't think we can just definitively, say something about whether or not aspartame causes anxiety. It may well impact it. Okay, it sounds like there's something here, but we don't know yet. Okay, moving on, we're going to go on to stevia, everybody's favorite. Stevia and monk fruit. Okay, I'll do them separately, but these are everybody's favorite because they're natural, Dr. Low. Okay, all right, let's just see. Stevia is from the leaf of the Stevia rebaudiana plant, and I've actually tasted it from the leaf. It's pretty cool. And the chemicals in the plant are steviol glycosides. Okay, the most abundant is rhodioxide A and stevioside. Okay, and so there are all these different types of stevia compounds that we'll just simply call stevia glycosides, and they have a main skeleton, and then we have these sugars attached to that main skeleton. So you can have monosaccharides and disaccharides, different sugar units attached to this main skeleton. That's why it's called steviol glycosides, okay, the sugars. And basically these are, going to go into the gut, and they're metabolized by colonic bacteria there. And the final degradation product doesn't matter what glycoside we're talking, right? Which of the stevia glycosides we're talking about. For all of them, the final metabolic product is going to be steviol. So it all ends up as steviol. So you consume the stevia and it goes into the colon, and it's there that the gut bacteria work on it, and they break down the sugar units, and they use the sugars there for their, fuel and metabolism, right? And then a small amount of that stevia does, get to the liver, and then it's excreted again, probably through bile, and gets back into fecal matter, and then you pass it out. So that's basically stevia there. Now, many years ago, when I was looking at stevia, I was a little intrigued because it seemed like it did have some liver protective functions, right? That it seemed to protect against fatty liver, for example, and liver injury. So, I'd always thought, yeah, I think maybe stevia would be the way to go. It doesn't really get absorbed. The gut bacteria kind of chow down on it, and then on top of that, it may protect the liver. And then there was this one study out of most of the ones that seem to suggest that it is liver protective. There's one study I saw, thinking now just from memory, it was actually using sucralose and stevia. So it wasn't just, I don't think they combine the two, and they might have had one group that just used the stevia. But this was a study that actually showed liver and kidney damage, quite profound liver and kidney damage in mice that had been given sucralose and or stevia, I believe, for in their drinking water. And again, just for the same reasons that I explained earlier, it's hard to know. Was it mainly the sucralose? What effects did the stevia have? Hard to sort that out. That was the only one. Most studies seem to suggest a liver protective effect from the stevia. But think about this. If the gut bacteria are chowing down on your stevia and breaking down the glucose units there, it probably is going to change the ecology of the gut if you consume a lot of stevia as well. Okay? Monk fruit. Monk fruit is also from a plant, a fruit actually, and I'm familiar with it only because growing up in Singapore, whenever you had a cough, you'd always be told to drink this syrup that was made of monk fruit. Now, anytime I coughed, just one cough, and that whole bottle comes out. You gotta drink this. And I hated it. I hated it because it was just cloyingly sweet. It was just, and I always tried to avoid, taking some of that syrup. So that's the monk fruit, and it's got many of these compounds called moghrosides in it. And there are different types of moghrosides, and also the moghroside content is going to shift and change as the fruit is developing. Now, some of these moghrosides are bitter, some of them have no sweet taste at all, and then some, especially in the late stages as the fruit is ripening, right? Then you have certain moghrosides appear at that stage of fruit development, and then those moghrosides are really sweet. So you kind of have to time, if you're trying to harvest these moghrosides from the monk fruit, you have to time the stage of fruit development, because different moghrosides have different sort of profiles, and some are, like I said, bitter, some are not, just no taste at all. So the most common, I think, is moghroside 5, which is generally, I think, what is used in these monk fruit sweeteners. Now, monk fruit, okay, this seems to be the wonder drug. or the wonder sweetener, okay, because it has antitussive effects. So turns out, yeah, I wasn't crazy, that it does seem to help with coughs and phlegm production. And it also is an antioxidant, okay, and that's a good thing. Mops up some free radicals. And interestingly, most interesting to me, it's been found to lower blood sugar and decrease hyperlipidemia. And this is thought to be through AMPK activation. So, there's some studies that suggest it may even help lower blood sugar, which, that's probably the wonder sweetener then, if it can do that, right? So not only are you not consuming sugar, but you're also lowering your blood sugar levels. So who knows? That may be the case, but it's the newest kid on the block, and we still, again, need a lot more studies on these mogicides. Okay, and then we come to this class that I want to talk about, and this would be the sugar alcohols or polyols. All right, I think it's important to talk about these sugar alcohols because a lot of times when people go low carb or try to do keto on their own, they will reach out to these sugar alcohols as their sweetener of choice, or if they're buying keto products, processed keto products, that they see in the supermarket, in the store, a lot of these will contain the sugar alcohols. So if you remember from the episode I did on carbohydrates, they're just really sugars with the alcohol groups in them. And the ones that I think I will really focus on would be sorbitol. I'll talk a little bit about maltitol, xylitol, and also erythritol. Okay, sorbitol. Sorbitol is actually made in your body as part of the polyol pathway. And you've heard me mention this a few times now in the episode on advanced glycation products, in the fructose episode as well. So glucose, when you have a lot of glucose in your body, then we can take that glucose and we can convert that glucose, enzymatically convert it to sorbitol, okay, this sugar alcohol. Now, sorbitol has a huge osmotic effect, so it draws a lot of water to it. And that's why if you consume products that have a lot of sorbitol, then you are likely to get diarrhea. And, physicians will remember that when someone comes into the hospital with high potassium levels, you give them a nice hefty dose of sorbitol and they're just going to have diarrhea and poop out the potassium. Yeah, that's what K-exolate is for, right? So we've used sorbitol to induce diarrhea in patients. Now that sorbitol in your body is also now converted by another enzyme to fructose. Yes, the F word. So that's how glucose gets converted to fructose, and it can go backwards too. The fructose can be converted to glucose as well. So we take the glucose, we make it into sorbitol, and then we have another enzyme that takes sorbitol to fructose. There are some tissues in your body that don't have that second enzyme, and so they really have a limited ability to take that sorbitol and convert it to fructose. And those are like your retina and lens in your eye, right? And your kidneys, for example, and also nervous tissue. Okay? And this leads to serious consequences because now we can't convert that sorbitol to fructose, and so we have accumulation of sorbitol in those tissues. And I told you sorbitol is going to draw fluid in, and as a result we're going to damage the tissues that we're talking about. So we're going to damage the eye. So that's how we get diabetic retinopathy. We can damage the kidneys, right? Diabetic nephropathy and diabetic neuropathy is a result of this sorbitol accumulation. We draw a lot of fluid to it, and then we damage the membranes and so forth. Okay, so that's sorbitol in the body. It's highly inflammatory. It's not a good thing. So if you're consuming something with a lot of sorbitol in it, not only are you going to have this diarrhea effect. Now my question is, and I don't think this has been studied, right? What's the effect of sorbitol on the intestinal cells themselves, and also the some of the gut bacteria? Is there conversion to fructose within the gut bacteria? Are we having any? It's not supposed to be absorbed, but actually some of the sorbitol is absorbed. And in that case, is that sorbitol then converted to fructose? I don't know. So these are the questions that, I kind of wonder about. Now, the other thing with the sorbitol is that it will get fermented in the gut and converted to glucose, which is why I think it can also be converted to fructose in the gut. And then in that case, the colonic cells can take up the fructose as well, right? Okay, so we can ferment the sorbitol, and this will lead to a lot of digestive discomfort. So people will have bloating and flatulence, gas, if they're consuming a lot of sorbitol. I tend to limit, a lot of my patients like to use the sugar-free gum. It has a lot of sorbitol in it, so we usually get our patients to limit the number of gum pieces that they chew per day, right? But again, all those keto foods often will have these sugar alcohols. The other one is maltitol. That's used quite a bit, right? Now, the whole idea is that it's, these substitutes for sugar have quote unquote low glycemic index, right? And as a result, we're not going to have an insulin spike. So that's why you want to use them instead of sugar. But with maltitol, it turns out the glycemic index is around 52. And just for reference, the glycemic index for sugar, table sugar, is 65. So I'm not sure we're doing anything by substituting maltitol for table sugar, right? I mean, using maltitol instead of table sugar. So, it's, again, I see maltitol a lot in those keto products that are available in the store. Xylitol is actually made in our bodies as well. Xylitol is part of the pentose phosphate pathway, and this is a pathway that is very useful for building, cells, for making things, right? So if you are in a proliferative phase, you are also repairing tissue, then we can harvest a lot of let's say carbons and energy from the pentose phosphate pathway. Xylitol is in that pathway, and it's generally just a metabolite in the pathway. What we find with these sugar alcohols, a lot of times they'll say that they're good because they don't give you dental caries, so it protects your teeth. Xylitol is one that they've seen, can be protective against dental caries. And so if kids would use xylitol instead of sugar, I don't know how much xylitol they should be using in general. I think we should still be careful. But all the sugar alcohols don't bring about dental caries, okay? So xylitol is one of them. And then there is erythritol, okay? So let's just talk about erythritol. I'm going to tell you straight off, I'm biased. It is my favorite sweetener. It is my sweetener of choice, and so you should know that. All right, erythritol is also made in your body. It is also part of the pentose phosphate pathway. Okay, so when people ask me in the past, they would say, what sweetener would you use? Well, if I use it, probably would use erythritol. So it's 4-carbon compound. The xylitol is 5 carbons. It's the smallest of the sugar alcohols. The other thing about it is that it's symmetric, right? So there's only one form of it. Erythritol, I said, is made in the pentose phosphate pathway. It's excreted in the kidneys. Really, it is the only sugar alcohol that is not fermented in the gut. It gets absorbed and then eventually is excreted in the kidneys. So I told you that the sugar alcohols generally give you diarrhea and gas and all kinds of abdominal discomfort. And that doesn't tend to happen with erythritol because it's cleared in the kidneys. And the other thing about erythritol is it does not glycate. It doesn't have the carbonyl group, okay? So it's not going to be involved in those glycation events. So, the sorbitol, maltitol, they have been found to be involved in glycation events. And sucralose too. Remember, sucralose is very similar to sugar, table sugar. And it has been found to be involved in glycation events, okay? But not erythritol because it doesn't have that carbonyl group, okay? And so it's also been seen to be somewhat of an antioxidant in some studies. Okay, I'm not sure about that. But I think that if you're going to cook, for example, and you're making some kind of a glaze or, you are using some kind, you want to sweeten up your food. I know, what do I know about cooking? But I know my patients, they like to add, something sweet to what they're cooking, depending on the recipe, right? Well, if you're using the erythritol, you're not going to increase glycation events. So if you have to, then probably that is the best one to use. Now, erythritol, the brand name that people really associate with erythritol is Truvia, but Truvia is actually erythritol with stevia. And it's rare you have erythritol on its own because it's actually only like 60 to 70% as sweet as sucrose. Okay, so it's kind of almost 1-to-1. And it has this weird cooling effect in your mouth, which is good for eliminating any aftertaste of other types of sweeteners. So they like to combine it to eliminate any aftertaste effects of other sweeteners. They don't like to use pure erythritol because it's very expensive to produce, right? Very costly. So they kind of just always use it combined. You can get pure erythritol. You can purchase it. It tends to be costly, but I've certainly purchased it at an online store named after a rainforest in South America. All right, so, you can get the erythritol. All right, I think we got through that. Oh, okay, I just want to emphasize that, the erythritol, there are no studies saying it is the best sweetener to use. That was just based on my own preference, my own bias. I just looked at the chemistry and it seemed to make sense to me, which is why I personally prefer using erythritol, but there really aren't studies that say this is the best and this is what you should use, okay? Just want to make that clear. One other thing I want to add, I forgot to say about xylitol that might interest some of you. in some studies, xylitol has been shown to prevent ketogenesis. So, you can't actually go into ketosis with the use of xylitol. And it seems to be because it somehow restricts access to free fatty acids, endogenous free fatty acids. If you give exogenous fatty acids, it doesn't happen. You can go into ketosis. So it's unclear then. Those were, again, animal studies. Okay. So that might be, again, of interest to people who are maybe trying to do a ketogenic diet or are trying to go low carb there, and they're using some of these sugar alcohols for that. Okay. Remember in the beginning, I said that, the hope was with these artificial sweeteners, we could, decrease obesity and decrease intake of sugar in people and hopefully get people to a healthier place. And well, it hasn't turned out that way. Well, I think this is because if we look at studies, there is a neural preference for sugars, okay? So the gut-brain axis, it turns out, knows when you are taking in an artificial sweetener versus the real thing, okay? And when it detects the real thing, when it detects sugar, then it's going to signal, right, to the brain that, okay, we have sugar here. And this is independent of the caloric or energy value of the sugar, because they've used, other compounds that actually are structurally similar to sugar, but have no caloric value because it cannot be metabolized, right? And the brain will still register that we have a sugar-like substance in the gut, right? And these non-nutritive sweeteners don't give the same response. So it turns out that, first of all, you can't fool your body because it knows when you're having the real thing or not. And then it turns out in other studies, they found that, okay, people who are consuming, let's say, soda drinks, diet soda drinks, or other products that use these artificial sweeteners, it turns out that through the rest of the day, they kind of make up for the sugar intake in other foods. So they're not having sugar in those products, but somewhere along in the day, they're still getting in the sugar. And I think it's because your brain knows, you can't fool me, go get the real thing. Okay, so all these efforts to make these, substitutes, but in the end, you really can't fool your body. So time for our wrap up. Okay, let me see if I can get the wrap up in my head. We talked about non-nutritive sweeteners. We talked about how they determine the acceptable daily intake. And then we looked at the different groups, right? One group is absorbed but not metabolized. That would be your ACE, your sucralose, your saccharin. And then you have another group that is metabolized, and we have there your aspartame, and we also have stevia there as well. And then we have the whole sugar alcohol group, which, there's some absorption, but most of it just gets passed to the colon, except for erythritol that is absorbed and is renal cleared. And we also went off a little bit on gut microbiome and why it's really hard to come to any definitive conclusions based on just the gut microbiome itself. And certainly, the more information we have, the better, but it's still a long way off before we can figure out how the microbiome itself is, shaping the immune response and so forth in the gut. Okay, I am so glad I got through this episode. As I said, it's not my favorite because you can see it's very messy, right? And I have so many questions, and there's so many things that are not clear to me. And I thought, yeah. So when someone asks me about, what do you think about artificial sweeteners? I'm like, ugh, it's messy. Okay, but we got through it, and I am so happy. So before I end, I'm just going to say, I hope you will support this podcast, that you will support this channel by liking and subscribing. It does help the algorithm, especially on YouTube. And please check out my website, vlmd.com, vyvanelohmd.com. And there you can subscribe to my newsletter. But the other thing also is that you can look up my schedule for live stream events. And I love to get people's questions at the events and hear from them what they'd like me to talk about. I pretty much like to talk about everything except artificial sweeteners, and we're done with that, and gut microbiome. So those are the two big ones that, you know, I maybe hesitate a little bit about, but everything else is pretty fun for me. Okay, so I'm looking forward to seeing you at the next live Q&A. But until then, signing out from VLMD Rounds, I am Dr. Vyvyane Loh, and I sing the body electric. Bye-bye.